Hello everyone. Welcome to the network seminar series hosted by the Center for Networked Intelligence at the ECE and RBCCPS IASC. It's my pleasure to introduce today's speaker, Professor Prasenjit Chanak. He will be speaking on data-driven next-generation wireless networking, harnessing AI for superior performance and security. Professor Prasenjit is an assistant professor in the Department of Computer Science and Engineering at the Indian Institute of Technology, BHU, Varanasi. He earned his MTech and PhD degrees in information technology from the IIST Shibpur, India in 2011 and 2016 respectively. He leads the IoT and Embedded Systems Lab at the IIT BHU Varanasi, where his research focuses on various aspects of ubiquitous and pervasive sensing systems and the development of embedded applications. He led the several government-sponsored projects from the organizations like DST, DRDO, ICSSR, and SERP. Professor Prasenjit is also a recipient of CSIR National PhD Fellowship from the Government of India and the Chester Hall Awardee from IEEE Transactions on Consumer Electronics, Best PhD Thesis Award from Computer Society of India, Young Scientist Award from the Department of Science and Technology, Government of India, and the Best Paper Awards from several conferences. His primary research interests include wireless sensor networks, Internet of Things, cloud computing, cyber physical systems, machine learning, and consumer electronics. We request the audience to keep your microphones on silent for the duration of the talk, except when asking questions. And for questions, feel free to unmute yourself and ask directly or type them in the chat box. We will relay your questions. Over to you, Professor.
Thank you, Srinivas, and good evening all. So today I just discussed regarding the data-driven next generation wireless network, as title suggests. In this particular discussion, I will discuss that what are the different issues present in the different layer in wireless networks and how these issues have been solved or will be solved through the different AI technology. Okay. Now, whenever we're talking about next generation wireless networks, in case of the next generation wireless networks, huge amount of data captured by different devices, and this data transferred to the remote location where data is processed and analyzed and make the different decision. Okay. In this particular slide, I have shown one picture where different physical object connect to the internet. And whenever different physical object connect to the internet, this physical object generate huge volume of data. And this data how reach to the destination with minimum delay, high performance, that we require to taken care for next generation wireless networks. Property of the next generation wireless networks. What are the demand of the next generation wireless networks? Ultra high data speed, ultra low latency, massive device connectivity, high reliability and availability, edge computing, and decentralized processing, energy efficiency, security, privacy, flexible, programmable networking. These are the major property that require for next generation wireless networks. Now, whenever we're talking about the different layer for a networks, then we just look this network stack. We have physical layer, data link layer, network layer, transport layer, and upper layer. But whenever we're talking about the traditional wireless network methodology, these are not capable to handle huge volume of data. Okay, those are transferred from the different object to the central server for monitoring purpose. That's why what happened, we need data-driven technology to boost up our next generation wireless network performance. Okay, that is the important of AI technology. So AI and machine learning offer a data-driven approach to enhance performance and efficiency and security of the networks. Because whenever we're talking about that next generation wireless network need a high performance routing strategy, high performance that security protocols. These are the requirement, and this requirement we can fulfill through AI technology. AI technology include, as we know, that different supervised, unsupervised, and reinforcement learning across all network layer, improving throughput, security, energy efficiency while addressing future challenges in wireless networks. Now, before going to the detailed discussion, we are basically look that basic concept or taxonomy of AI and machine learning techniques. That machine learning techniques can be divided into three different categories: supervised, unsupervised, and reinforcement learning. And whenever we're talking about the supervised learning, include classification and regression algorithm. And if we're talking about the unsupervised learning does not need any label data, which is classified into dimension reduction, clustering, and generation that generative algorithm. And whenever we're talking about the reinforcement learning, then reinforcement learning is categorized into model based and model free algorithm. So these are the basic taxonomy of AI and machine learning techniques. Now, whenever we're talking about the network stack, then first layer is physical layer. And if we're talking that the application of AI to solve the physical layer issues, then first thing is that channel coding. That AI technique basically used for signal processing and channel estimation. In that case, what happened? Machine learning algorithm predict and compensate for the noise interface and fading in wireless channel. A technique like deep learning can improve the channel estimation, okay, ensuring high data rate and better signal quality. Then we can use AI techniques for adaptive modulation and coding. AI-based algorithm dynamically adapt the modulation scheme and error correcting code based on the network condition. Another issues that we can solve through AI in physical layer, that is the interface management. Machine learning model can identify interface pattern and implement solutions such as prefarming and interference cancellation on power control and minimizing the signal degradation and maximizing coverage. So these are the physical layer issues that we can solve through AI techniques, or other word you can say we can boost up whatever the requirement of our next generation wireless networks through AI techniques in this particular direction. Now, that next layer is the MAC layer performance. In case of the MAC layer performance, that power allocation and energy management is most important. And whenever we're talking about the power allocation and energy management, we can use deep reinforcement learning for high secondary that help secondary user predict primary user power allocation in cognitive radio network and improving spectrum efficiency also. Also, we can use deep queue networks that basically optimize mobile network sleeping roads by learning the traffic pattern. That basically reduced energy consumption. That is the most important things for next generation wireless networks. For next generation wireless networks, we always try to reduce energy consumption rate. Okay. So for this in MAC layer, we can use deep queue networks for effective management of sleeping schedule. Okay. Next issue that basically present in MAC layer that we can also solve through that AI techniques, that is the spectrum and access management. We used multi-task deep learning for enhance non-orthogonal multiple access by modulating and spreading symbol and detecting efficiently, enabling better signal decomposition in 5G and next generation networks. And we also use that the multi-agent deep reinforcement learning for optimization dynamic spectrum access by learning the best time slot for transmitting, maximizing data rate and improving overall network efficiency. Next layer is the network and transport layer. Okay, as a computer science background, I just focused on this particular layer, that how we can use AI technique to solve different issues. Those are related to networks and transport layer. Whenever we talking about the networks layer, in network layer, we can improve routing efficiency using different AI techniques. Okay, and we can also apply AI techniques for data aggregation and collision control. Okay, so these are the major sub area where we can use AI technique for improvement purpose. Okay, and that is basically fulfilled that next generation wireless networks requirement. Okay. Now, whenever we talking about that the network layer, in network layer for routing purpose, if you look that particular picture here, different network, these are the sensor network, these are deployed for capturing data from the different monitoring area. Okay, this sensor capturing data from the surrounding environment and transmit this data to the base station for further processing purpose. Okay, now whenever data travels through the networks, wireless networks, then this data is basically faces, or network is basically faces different challenges. Okay, whenever we talking about the fault in wireless network, fault occurrence probability is much more compared to traditional networks. And whenever fault is occur, then that the performance of the network is basically degrading. So that's why we can apply AI technology to detect fault, that where this fault is basically occur and which node is basically suffer by the different fault. If we just detecting this fault, then we can improve the performance of the networks. So that is the one area, sub area, that coming under the network layer, we can apply AI technology to improve the network performance. And another is that the congestion control, whenever huge data transfer from the source to destination, then what happened, that the congestion is the major issue. Some of the application demand, whenever one event is occur, suppose that if we're talking about the healthcare application, in healthcare application, normally we develop one networks that capturing physical parameter of the patient, and certainly if any emergency occur, then what happened, we require to transfer this data in fast way. Okay, on that case, we require a proper congestion control mechanism. Otherwise, what happened, that data not reach to the destination in proper times. Okay, so these are the issues that we can solve through AI techniques. And another thing, that is the load balancing. Load balancing in terms of the traffic management. Okay, we can plan a AI based techniques, or we can apply a AI based techniques for next generation wireless network that basically capable to handle that the huge traffic that basically generate within the networks, and that also reduce the latency of the data transmission. Okay, so these are the few issues that I have mentioned here. Excluding these, so many other issues also present within the network and transport layer. These issues we can also help we can also solve through AI techniques, different AI techniques. Now that whenever we're talking about the AI for performance at network layer, then what happened that the routing and traffic engineering, that we can use deep reinforcement learning for betterment or improvement of routing performance, congestion control, reinforcement learning. Excluding this, we can also use the different other AI algorithm also. Okay, I have mentioned few AI algorithm here, but excluding this, we can use that different AI algorithm for solving these issues. Okay, data aggregation in mobile ad hoc networks. Now, here we have done some work that is basically solve that the fault tolerance data routing scheme. Whenever we're talking about the wireless sensor networks, in wireless sensor networks, what happened that basically two types of fault occur within the networks. One is node fault, another is link fault. When node fault is occur, then what happened? Whatever the path basically specified for data transmission, this due to lack of this path, the data is not reached to the destination. Okay. And if link fault is occur, then also that same thing is happening, that data is not reached to the destination point. Okay. So in this particular work, what happened, we basically first detect that fault, and after that, what happened, we proposed one energy efficient data collection mechanism. Okay. Under this particular energy efficient data collection mechanism, what happened that one mobile SIM start moving from the base station and visit throughout the networks, collect data from the all node, and after collection of this data, that node is that mobile SIM transfer this data to the base station. Okay, in this way, what happened that we basically reduce transmission distance of the sensor node. That's why energy consumption rate of the sensor node also reduced. Okay, so in this particular work, we use multi-objective deep reinforcement learning based algorithm for fault tolerance in WSN. And the main objective of this work is to detect that the faulty node with high accuracy and less overhead. Whenever we're talking about the wireless sensor network, that if we proposed one algorithm that basically that pass so many overhead message, okay, that is not good for the networks. Okay, that's why whenever we're talking about the fault detection and faulty node identification algorithm, that must be passed that the less control packet to detect faulty node. So that also required to take care. Okay. So this work focused on the reliable data transmission after fault detection. And finally, a mobile SIM is used for energy efficient data gathering that significantly improve network lifetimes. Now, here, whenever we're talking about that the fault, okay, in wireless networks, that fault can be classified into four different categories. One is the energy management based fault. In energy management based fault tolerance mechanism deals with the energy consumption of the smart sensor node to prevent premature death of the networks. Another issue that basically occur due to the fault within the networks. What happened whenever fault occur within the networks, then sometimes network is basically divided into different isolated segment. Okay, and whenever network divided into different isolated segment, then what happened? Then data is not properly reached to the destination node, and automatically quality of the networks is degrading. Okay, so that is the effect of fault. Okay, and another issue that is coming under the fault tolerance, that is the flow management. the flow management based fault tolerance mechanism ensure continuous connectivity in case of any node and link failure. That means whenever link failure is occur, then that the connectivity of the other node that also disturbs. On that case, whatever the optimal path we basically decided for data transmission, this optimal path is basically changed. Sir, have you any questions?
I have a question.
Yes.
Yeah, every problem that you have enunciated in the last couple of slides has had standard solutions for a long time, using standard approaches, using traditional techniques. So
Yes.
can you tell us in what way AI or machine learning has enhanced those techniques, and in what way what you are doing complements those techniques? Are those techniques completely discarded and you have completely new techniques? So can you explain, because you're just describing the problems and telling us in a very high level manner what the possibilities are. Can you tell us in a little bit more detail in comparison with the traditional ways of doing these things? Thank you.
One thing is that whenever we're talking about the traditional method, in case of the traditional method, if we look that if the network size and data within the network is basically increased, this traditional method is not perform well. Okay. If we just talking about the fault detection accuracy, if we apply the traditional method for fault detection in a large size network where the large data is basically generated, then the performance that the fault detection accuracy is not so good. Okay. And sometimes what happens that the traditional that method, they are unable to prevent that the partitioning of the networks. Okay, that I have told that how the network is basically partitioned into different segments. Okay, and that's why we need AI based techniques. That AI based technique is basically consider lots of parameters. Okay, during the fault detection, and due to consideration of lots of parameters, okay, then what happened that the accuracy of the fault detection techniques is basically increased. Okay, so that's why AI based techniques is one good option for next generation networks protocol development. Okay, so that is the significance of the AI here. We can solve that the next generation, whatever the problem present in the next generation network through the traditional method. But what happened that whatever the performance required for the next generation network, these are not fulfilled by the traditional method. Okay, that's why we need AI based techniques. That is basically depending on the that AI based techniques taken the real time knowledge from the environment and make the decision. Okay, that improve the efficiency of the protocol, whatever the protocol we basically proposed. Okay, that the flow management based fault tolerance mechanism ensure continuous connectivity in case of the any node and link failure. It also governs the optimal flow of the data within the network that significantly improve the overall performance of the networks. Now, another types of fault tolerance that basically occur within the WSN, that is the data management. Data management based fault tolerance. Fault tolerance mechanism deal with the collecting and aggregating data by the sensor node or cluster head. That means if we're talking about the traditional energy saving method for WSN, then cluster based data routing is most popular. But in case of the normal cluster based data routing scheme, what happened that the cluster head collect data from their cluster member node, and after aggregation, this data is transmit to the base station. Now what happened if that cluster is going to the fault, then we require to shift that the cluster head role from a particular node to the another node. That is basically consume lots of energy. Okay, these things we properly managed through the AI based techniques. Okay, And coverage and connectivity management based fault tolerance, that the coverage management based fault tolerance mechanism deal with the coverage issues where the active sensor node preserve the maximum number of alternative paths with maximum coverage. Okay, this mechanism, that maximum packet delivery to the base station, is guided by the selecting the alternative path. Now, in our proposed scheme, what we have done, that first we select optimal rendezvous point. Okay, I have already told you that in our proposed scheme, we basically introduce a mobile sync based data collection mechanism. In case of the mobile sync based data collection mechanism, what happened, that mobile sync start data gathering process from base station and visit different location within the network and collect data from the surrounding node, and after the end of the data gathering tour, what happened, the data is basically reach that uploaded to the base station. Now, whenever that mobile sync based data gathering scheme we required to propose, we first required to select that the rendezvous point. Rendezvous point means that a single point where mobile sync stay and collect data from the surrounding environment. Okay, so because if that mobile sync visit each and every node and collect data, that is basically increase data collection delay. Okay, that is also one issue. That's why what happened, we basically first select some rendezvous point where mobile sync reach and stay, collect data from the surrounding environment. Okay, and after that, in that particular proposed scheme, we also propose a cluster formation phase, a cluster formation mechanism. After that, intelligence fault tolerance using multi-objective deep reinforcement learning and efficient data gathering using mobile sync. Now, first phase, whenever we're talking about the first phase, for this particular work, we are basically considering a heterogeneous network. In this network, we deployed two different types of node. One is the normal sensor node, another is the spatial sensor node. Spatial sensor node capacity is more compared to the normal sensor node. Capacity means that the energy and transmission capacity, okay, transmission range of the spatial node is high compared to normal nodes. Okay, and that is basically doing for that the cost purpose. Initially, normal nodes are deployed randomly in square-shaped monitoring field, and after that, maximum coverage location problem identifies the best optimal location for that spatial sensor node. Okay, and whenever we want to identify that the optimal position of the spatial sensor node, then we use that the MCLP, where we find P location for n candidate by ensuring the maximum coverage of the candidate by minimizing distance between all location and candidate. In the proposed work, this algorithm is used to identify that the optimal position for that the spatial node placement based on the total number of sensor node deployed in an environment. And this sensor node become the cluster head for each group here also. Okay. Now, whenever we're talking about that MCLP based optimal RP selection, RP also basically that the nearest location of the spatial node. Okay. Now, how these things optimal position is basically selected, that the set and indicator, that sensor node, normal sensor node basically identified by that the capital I set, and RPs are basically represented by the capital J. Okay, and after that parameter we basically consider that HJ, total weight at RPJ, and DIJ, distance between sensor I and RPJ, and R is the maximum range of RP. And decision variable, here we have considered decision variable, that if a sensor is basically located in a specific location, that is denoted by 1, otherwise 0. Okay, then that means there is no sensor. And similarly, whenever we're talking about the RP, that means the spatial node, that if one sensor is attached with the spatial node, then it is basically denoted by 1, otherwise 0. Okay, and based on that, we basically said that the optimal function and respect to this Euclidean distance and maximum capacity of the spatial node. In this way, we calculate that the optimal position of the spatial node, okay, and cluster basically from based on this particular spatial node position. So phase 2, that is basically describe cluster formation. Okay, in that case, what happened that after deployment of spatial node to other optimal position, they broadcast, spatial node basically broadcast a request to join message with their ID, location and residual energy within its range. If any normal sensor node receive request to join message, then it send a response message to the corresponding that spatial nodes, and response message contain the ID, location, residual energy of the normal sensor node. After this process, all the normal sensor node are basically joined with the nearest spatial node that is acting as a cluster head, and nearest region of this spatial node also is basically a rendezvous point. Within the nearest region, one point is basically selected as a rendezvous point. And here we consider that the spatial node position is basically a rendezvous point where mobile sync basically reach, stay and collect data from the cluster head, and cluster head collect data from the cluster member node. If some node will be left to join any spatial node, then this normal node are treated as an isolated node. Okay, during the cluster formation, what happened that if some of the node are unable to join that the spatial node, then what happened? Those nodes are not capable to join that the spatial node. These nodes are basically treated as a isolated node. Each isolated node broadcasts a help message to all other normal node in their communication range. If any normal node receive a help message, normal sensor node, then normal sensor node reply with response message with their ID, location and residual energy. Finally, isolated node join nearest normal node with high residual energy and least distance. Okay, whenever that normal sensor node, those are already joined with its best spatial node. Okay, and if this normal node received help message for any other isolated node, then what happened? Sent a response message. Okay, based on this, what happened that isolated node basically select nearest and highest residual energy node to join that the nearest cluster, okay, or join with the spatial node. The spatial node aggregate the collected data from its member and transmit the data to the MS when it comes to the data collection. Okay. Now, third phase, fault tolerance phase using multi-objective deep reinforcement learning. If a fault occurs in any sensor node, then an intelligence MODRL based algorithm is used to detect the fault in sensor node. In the fault detection phase, sensor node act as an agent to detect any fault within the networks. The first objective is to minimize message overhead. Whenever we're talking about the fault detection algorithm must be used minimum overhead. Okay. So that's why we just fix that first objective is to minimize the message overhead during the fault detection phase. And The second objective is to minimize the communication delay, and the third objective is set to maximize the network throughput. Since all the objectives are contradictory with each other, thus the problem is solved using the Pareto optimal policy set. Okay, here what happened? We are basically using Pareto optimal policy to solve this objective. Whatever the objective, we are basically used for high throughput and delay minimization. Okay. Now deployed sensor node act as an agent and maximizing the overall performance by optimizing the conflicting objectives. The agent deal with the multiple objects such as minimizing the message overhead and communication delay. Furthermore, that the agent also maximize the throughput by timely detecting of faulty node. In this particular work, that many wireless sensor node with large state space in the MDP framework are considered. Therefore, what happened? We are basically using a double deep queue networks is used in the MODRL algorithm for optimizing queue value, which give the highest reward by minimizing the overall estimation. Okay. That whenever we're talking about the traditional that is method, those are basically used for the networks. And on that case, what happened? Generally, traditional method are basically work in a single objective. Okay, if they work, they are only focusing on the energy optimization. Okay, and some of the traditional, they are basically focusing on the throughput improvement. Okay, but if we just used AI-based algorithm, then we can consider that the multiple objective. Okay, and we basically optimize our protocol based on the multiple objectives. The DDQN consists of the two identical deep neural networks. Now, the isolated node transmit their data via normal sensor node to the nearest spatial node. After receiving the data, that the normal sensor node sent an acknowledgement message to the isolated node. The acknowledgement message contains node ID, location information, and reschedule energy. If normal node did not respond with a threshold time, then isolated node declare the non-responding normal sensor node as a faulty node and immediately join a new normal sensor node. Okay, suppose that one isolated node is basically transmitting a data, and after some times this isolated node does not receive any acknowledgement packet. Then what happened? This isolated node basically treated that the next of normal node that basically help to transfer that isolated node data to that spatial node, that means cluster head. These are in faulty state. That's why on that case, what happened, that isolated node is basically joined with the other normal node based on the distance and high residual energy. Efficient data gathering using a mobile sync. Next step is that the data gathering phase. Okay. In data gathering phase, what happened, that mobile sync use the information stored by the base station during the data gathering process. Before starting data gathering tool, MS collect the optimal path information from the base station. Okay, and base station compute shortest data gathering path using TSP with Christopher heuristic, and the base station start its journey from that mobile sync start its journey from base station, visit each that spatial node that is also acting as a cluster head, and the nearest location also denoted as a individual point or data collecting point. Okay, what happened? Whenever mobile sync receive a shortest path information from the base station, then mobile sync start it data gathering to and reach to the nearest individual point, that means cluster head, that means that special node, and collect data from the special node, and after collecting data from the special node or cluster head, it goes to the next cluster head. Okay, and in this way, whenever mobile sync collect data from the all cluster head, then back to the base station, and that whatever the data collected by the mobile sync, that is basically uploaded, and that mobile sync move through a optimal path. Okay, that is basically help to reduce that the data collection delay. Okay, now in this particular picture you can see that how data gathering is basically occur through the mobile sync. Okay, here what happened, mobile sync is basically visit each individual point and collect data from the nearest cluster head, and after collecting data it move to the next individual point and collect data from the nearest cluster head. In this way, after completing the data collection, it reach to the base station and upload the collected data. Okay, obviously that whenever we just basically talking about a algorithm, that we require to compare the performance of the proposed algorithm, that in our case we also compare our proposed algorithm with the state of the existing algorithm. That means that we are basically compare our proposed algorithm with the LSTM and GPS, PSO and HFDP with respect to this performance metrics: fault detection accuracy, false alarm rate, false positive rate, average energy consumption and throughput. Okay, here in this particular graph you can see that the fault detection accuracy of our proposed scheme is much more compared to the other algorithm. Okay, this is due to the use of AI based techniques for fault detection. Okay, in case of the AI based techniques, we are basically considered that multiple parameter for fault detection. Okay, similarly, this is the one scenario where we consider 100 node, and this is the another scenario here that number of deployed node is little bit more compared to that previous scenario. In second scenario, we basically consider 200 node, and for 200 node that our proposed scheme also show better performance compared to other existing techniques with respect to fault detection accuracy. False alarm rate, if we're talking about the false alarm rate, that false alarm rate also less compared to the other existing techniques. Okay, similarly in that dense networks, that whenever we're talking about the 200 node, on that case our proposed scheme also perform better result compared to the other existing scheme. Now that is the false positive rate. In case of the false positive rate, our proposed scheme also give that the better performance compared to the other existing techniques. Okay, and when we are basically checked performance of our proposed scheme in both case, that is whenever that 100 node are deployed and whenever that 200 node are basically deployed within the monitoring area. Average energy consumption rate in our proposed scheme is less compared to other existing scheme. It is due to the mobile sync based data collection scheme, because that mobile sync based data collection scheme basically reduced that the transmission distance of the special node, and due to the reduction of the transmission distance, what happened that the energy consumption rate of the special node that is reduced. Okay, and obviously network throughput, that if you look this particular graph, that the throughput of the proposed scheme is more compared to other existing scheme. This is due to also mobile sync based data collection scheme. Okay, and here comparison of the performance matrices if you look that whenever we're talking about the 100 node, if we're talking that the fault detection accuracy of our proposed scheme increase 16.5% as compared to the LSTM algorithm. Okay, if we're talking about the that false alarm rate, then that decrease 17.40% compared to LSTM and decrease 24.5% compared to GSPSO, and HFDC decrease 29.3%. In this particular table, you can see that due to the use of AI techniques and mobile sync based data collection scheme, that with respect to this parameter, we are getting better result compared to these three existing scheme. Okay. Now this is another proposed scheme. Here what happened, that indoor emergency evacuation system. In this particular application area, what happened, we developed a wireless sensor networks that capturing real information from the indoor environment, and whenever any emergency, fire like emergency is occur, then optimal path is basically provided by the systems based on the real information. Okay, what happened, that whenever fire is basically generated within the indoor environment, that whatever the people present within the indoor environment, they always try to move here and there for evacuation purpose. Okay, that's why so many accidents basically occur. For this, we propose one wireless sensor network based, or other word you can say this is the IoT related work, where we use these two technology, that wireless sensor network for data gathering, and that is also connected to the internet for monitoring purpose. So in that case, what happened, we are using AI based technology for data collection and that the optimal path calculation. So emergency evacuation system for dynamic fire region. Over the year, various evacuation techniques have been proposed for the fire emergency. Many existing techniques consider only the current fire hazard situation during the evacuation path design. They do not consider that the dynamic spread of the fire with time while designing an evacuation path. It may cause several detours and even trap individual in hazardous region. Okay. Hence, it is important to consider the dynamic fire spread while designing an evacuation path. In that particular work, we are basically considering dynamic spreading of fire. Okay. This particular proposed scheme divided into that 5 different phases. First is real-time data collection phase. In this particular phase, what happens? Sensor node, some physical sensor node deployed within the indoor environment, and this deployed node collect real-time information and send to a server. Okay. The optimal path initializing using reinforcement learning. Formation of the safety layer around the danger zone. Optimal path planning mechanism using a multi-objective gradable optimization algorithm and guiding evacuees to the nearest exit. These are the phases that is basically present in this particular proposed scheme. Now, phase 1, real-time data collection phase. Initially, the hardware modules are uniformly deployed in the industrial environment. Each hardware module is equipped with different sensors like smoke, gas, temperature, fire. Okay, these are the different sensors that basically equipped by the hardware module. Okay, this sensor equipped in the hardware module and sense the monitoring environment periodically. During an emergency, that the hardware module collect real-time data and transmit it to base station for further processing. That is the first phase. In second phase, optimal path initialization using reinforcement learning. After deployment of the hardware module and connection with the gateway node, the optimal path are identified using reinforcement learning. This work uses Q-learning, which is a value-based RL algorithm. The basic principle of any RL algorithm is to maximize the reward by taking a series of action at various state. In the proposed scheme, that hardware module are considered as an agent, okay, and exist location are their reward. During the emergency, that means whenever that we basically wants to calculate optimal path, then we just use this concept to calculate the optimal path, that nearest from that source to nearest exit. During an emergency, the optimal path are identified based on the current input scenario. If there is any change in the network topology, then the optimal path are updated accordingly. Okay, and phase 3, that formation of safety layer around the dangerous zone. In that particular case, what happened? We generate one matrix, okay, based on the fire map, okay, and we also consider that the different obstacles those are present within the monitoring environment during the optimal path calculation process. Okay, safety zones, that means nearest region where the fire is basically detected. If someone is basically present within that the nearest region, then what happened? We require to evacuate first. And if someone is basically present that the far away from this fire region, then this that person is required to little bit delay in that evacuation process. Okay, that phase 4, that optimal path planning mechanism using a multi-objective wolf optimization algorithm. After forming the safety layer around the danger zone, the proposed scheme identified the optimal path for each individual from their location to the nearest safe exit. Okay, the proposed scheme used the multiple objective wolf optimization algorithm for optimal path planning. In the proposed scheme, that the evacuation play the role gray wolf and the exist location are their prey. The primary objective is to find the shortest and safest path for each evacuees to exist the nearest exit. For this purpose, multiple objectives have been considered, such that safety layer, load balancing, and distance to the nearest exit. Okay, and guiding evacuation to the nearest exit. What happened? Whenever that the path is basically calculate, optimal evacuation path calculate based on the real fire situation. And during that the optimal path calculation, we also considered that the different obstacles those are present within the monitoring environment. After optimal path calculation, what happened? That that the optimal path information coming to the hardware node, and based on this hardware node is basically on LED light. This LED light indicating optimum path for each individual. Okay, so this is the overall mechanism that we have proposed for indoor emergency evacuation systems. And we basically compare our proposed scheme with the existing state of the art algorithm like ESPIM and CISM and ESAIOT. Now, these are the different scenarios that we basically create to validate our proposed scheme. So here black region basically indicating different obstacle, and during the optimal path calculation, this obstacle is basically preventing that the movement path of different individual. Okay, so now here that average distance cover with one exist. Okay, So if you just look that the distance that basically that optimal distance that provided by our proposed scheme, that is less compared to the other mechanism. And similarly, in whenever we talking about the two exist, then also that the optimal distance for evacuation, that is less for our proposed scheme. That average evacuation times for one exist, that is also less for our proposed scheme. And whenever we talking about the two exist, in case of the two exist, that the average evacuation techniques also list. Okay. And in this particular table, you can see that how our proposed scheme are basically so better performance compared to the other existing techniques. If we're talking about the scenario 1, where single exist point are basically present, on that case, average distance that is also reduced compared to ESBIM, and also that is reduced compared to the CISM, that is 25.25. That percentage is basically reduced. And similarly, that same thing is happening for ESAIOT based scheme. Okay, our proposed scheme are basically give better result compared to these things. Okay, similarly that the for scenario 2, scenario 3 and scenario 4, that same thing is basically happening. Now whenever we talking about AI performance at application layer caching, that the intelligent based station caching use a double code caching techniques to optimize delay and power consumption. Okay, so these are the area where we can use AI in application layer perspective for better performance. Okay, deep reinforcement learning for optimization model that network as an MDP with unknown transition and optimizing scheduling and transmission efficiency, application functionality and management. Okay, AI traffic classification that we can perform through different AI techniques, and AI driven network function verification in SDN, multiple agent deep reinforcement learning optimize device selection, routing and power allocation in IoT networks. And SDN for mobile agent cloud management, where we can use the deep reinforcement learning to optimize the video quality, transcoding, caching, bandwidth allocation and power consumption in SDN based video streaming. Okay, and in network layer perspective, these are the different attacks. To detect this attack, we can use AI techniques, that deep learning we can use for DOS attack detection in 5G network, loophole attack we can detect through that the deep learning for detection, and anatomy detection we can use that the support vector machine that give us the better accuracy and better result, and decision tree, random forest and k-means algorithm we can use for anomaly detection. And similarly that the AI for security at the application layer, application layer, that phishing, these types of attack we can use that Q learning to detect, and DDoS detection, that in that case we can apply AI techniques. Okay, for localization privacy we can use AI algorithm. Okay, obviously whenever we talking about the AI application for better performance in that next generation wireless networks, whenever we used AI, that AI have some drawback, that AI module in wireless network lack that interoperability, and selecting key features for better accuracy need more research. Okay, what are the parameter we require to consider that give us the better result? That is the most important things. Whenever we just basically apply AI technique to solve one issue regarding our next generation networks. and neural networks are complex and costly for IoT. Balancing AI with conventional method ensure the efficiency. Okay, AI in wireless network face security risks for adversarial attacks, robust defense are needed. Okay, these are the drawback whenever we just want to apply AI techniques for our next generation wireless networks. So whatever the work that I discussed today, this work we have published in that IEEE Internet journals and that the IEEE transaction on instrumentation management. So that's all. Thank you. If you have any question, then you can ask.
Thank you very much, Professor, for giving an informative talk. I would like the audience to pose your questions if you have it. I think there are no more questions, Professor. So let's end the talk today. Thank you very much, everyone, for attending the talk. And thank you once again, Professor, for accepting our invitation and delivering such a talk. Thank you very much.
Thank you. Thank you all. And future, if you have any doubt or any question, then you can mail me. This is my mail ID. And due to the short times that I just basically try to give a top view of all these problems. And if you want to work on this particular field, then during the work, you go to the details about this and you just apply AI techniques. Okay, thank you all. So
thank you. Thank you, everyone, and have a great evening.
Okay, thank you. Shall
Thanks,
I leave?
Professor. Yes, Professor. So, Professor, can you also share the slides with us? It will be
Okay,
helpful.
sure. I will share.
Thank you very much.